So we just revealed another lie to you, right? That insoluble products actually do dissolve to a certain extent. So that's what we're going to talk about with this specific type of equilibrium constant. And it's called KSP. So it stands for solubility product constant. And we're going to be able to calculate it anytime we form a precipitate. Okay, so it's basically giving us some information about the extent to which a, quote, insoluble salt will dissolve. So basically this is going to be the form. You're going to take your precipitate, which is going to be your solid, right? And it's going to be in equilibrium with its ions. So you'll have the cation, which will be dissolved, and your anion, which will be dissolved. And then whatever the stoichiometry is, right? Whatever the ratios are. If we do a specific example, like magnesium hydroxide. Okay, so that's a typical precipitate. The cation here would be Mg2 plus. Now, there's only going to be a tiny amount dissolved, right? And then hydroxide ion, OH minus, but you have to balance this, so this is going to be a 2. When you go to write the equilibrium expression, right, which you would just call K or KEQ or KC, you do products over reactants, so concentration of Mg2 plus times concentration of hydroxide ion, don't forget to square it. But take a look at your reactant. It's a solid, so it's not going to show up. So you're only ever going to have things in the numerator when you do these problems. And since we specifically are doing this for a precipitate, we're going to call this a KSP. Okay, so your KSP expressions will never have anything in the denominator because that thing is always going to be a solid precipitate. That means that the math with these is pretty easy, which is good. Okay, so let's do this example. What is the solubility of MgOH taken twice, so magnesium hydroxide, in moles per liter? So we just want the solubility in moles per liter. The definition of solubility is the maximum amount that can be dissolved. Well, we know that the maximum amount that can be dissolved is in a 1-to-1 ratio with our concentration of Mg2 plus ions. That's an important statement. I'm going to say it again. We know that the solubility of the MgOH taken twice is in a 1-to-1 ratio with the concentration of the magnesium 2 plus ions. So whatever concentration we get for Mg2 plus is going to equal the solubility in molarity for the magnesium hydroxide. Okay, here it's a 1-to-2 ratio, so you'd have to, cut this value in half to get the solubility of the magnesium hydroxide. Also, you see we're given a K value for the magnesium hydroxide, a KSP value. They're always going to be tiny, right? Because if it's a precipitate, not a lot of it's dissolving, just a little bit. So they're always going to be less than 1, sometimes substantially so. This is actually a pretty big KSP value. When you're doing these, here's a nice part. You're never going to have anything for your reactant, so you don't have to fill in your ice chart there. We're always going to assume, unless otherwise told, that we don't have any of our products yet. Okay, and you can see that the changes here are going to be easy. So we're going to have x here and 2x here. And then when we put those into the equilibrium expression, don't forget to square this one, we're going to end up with 4x to the third. And you might say, but that's, cubed. Yeah, but it's super easy because all you're doing is setting this equal to the KSP value. Okay, you just divide by 4, take the cubed root, and then you'll have your value, which is 1.3 times 10 to the negative 4th molar. Okay, so that X is equal to the concentration of Mg2 plus ion. If we needed the concentration of hydroxide ion, we'd have to double that. But that's also equal to the solubility of the MgOH taken twice. Okay, so when it's asking for the solubility, because they're in a 1-to-1 ratio, you got your answer here in molarity. Sometimes it'll ask for the solubility in grams per liter, in which case you just have to use the molar mass of the magnesium hydroxide. to make that quick conversion. Here's another example where we're asked to find the most soluble and the least soluble salt, and we're given 3 different insoluble salts or precipitates, right? These would be solid, mostly, and then a little bit of them would dissolve and dissociate into their ions. Then we're giving the corresponding KSP values. So at first you might just say, oh, well, this is the tiniest KSP value, so that means it's going to produce the least amount of product, the least amount of ions, so this would be the least soluble. This is the highest value, so this would be the most soluble. However, you can't just eyeball these and figure out what is the most soluble because these guys break up into different numbers of ions. Okay, so do me a favor, pause the video and write the dissociation equation for each of these, then the corresponding equilibrium expression, and use these KSP values to solve for the molar concentration or the solubility of each of these salts. And then that's what we're going to compare. So hopefully your work looks like what I have here. You wrote out your balanced equations, and then I didn't show my ice charts, I didn't show my substitution, but here's my final answer in each case, the molar solubility of each salt or each precipitate. Now, this is an apples to apples comparison, okay? So now for the most soluble, we're just going to find the largest value. So this is the largest K, all right? So we're going to deem the silver phosphate as the most soluble, okay? Not based on the KSP, but based on the molar concentration value. And then the least soluble, it looks like this, the smallest number we have here is for the MnS, for the manganese 2 sulfide. So this is going to be our least soluble. Okay, again, you have to look at the molar solubilities and do that comparison if they break up into different numbers of ions. So this one had 4 ions, this one had 2, this one had 2. Oh, well, these guys both had 2 ions apiece. So for those, you could actually tell right away that the MnS would be least soluble and that the iron 2 carbonate would be a little bit more soluble because it has a larger K value. But all bets are off when you're comparing things that have different numbers of ions, like the silver phosphate.